a bit strange. We're about a year into this thing of Zoom meetings every day, and I still forget to unmute myself about half the time, but getting used to it, I guess. I wish I could have been there to join you guys in person, but I'm happy to at least be able to share this work with you. I visited, I guess, a couple of years ago, and I gave some pieces of this talk, so I'd like to kind of give you an update on a bit of those things, and especially talk about this really exciting model that we've worked out for ways to improve our offshore resolution on megathrusts. But before I get started, I really want to take a chance to say thanks to all the collaborators and students and mentors and friends that I met all around Southeast Asia in the last 5 years living over there. This was a course that we taught in Myanmar, I guess about 1.5 years ago, and now it's hard to imagine that we'll be able to go back there anytime soon, and that's something really sad. So I'm not going to talk about the work in Myanmar this time, but these people were really instrumental in making that possible, and I'm so thankful to them, and I'm really hopeful that they're all okay. It's been really tough to even contact anyone since about February when the coup happened. So yeah, just keep these folks in your thoughts and prayers if you can. But let's talk about megathrusts. So we might be here on a beach with a beautiful coral reef. The ocean is wonderful. In Southeast Asia, I've definitely come to appreciate warm waters and snorkeling and beautiful reefs. But it's also a little bit inconvenient because we don't get to see geodetically what's going on the megathrust because it's so far offshore. And unless we have a lot of extra budget to put out the GPS acoustics, we're really, for the most part, still stuck with what we can see from the land. And during this quiet period, the interseismic period, we really have a limited ability to resolve what's happening offshore. And so I'll talk about what we can do in the interseismic period to improve our resolution, and then I'll also talk about what happens co-seismically and what can we learn about the fault friction and more of the material properties of the fault, not just the slip, hopefully using on-land geodetic data. So, okay, so the first part, interseismic slip. Well, you are all familiar with the megathrust and the earthquake cycle. So we have a stuck part of the fault. There's ongoing convergence. Over time, that convergence accumulates strain. That strain results in deformation of the ground, and we can see that geodetically. We can see horizontal and we can see vertical movements of the ground, and then it will be released ultimately during an earthquake. And the thing that I really want to emphasize here is that the tsunami requires the shallow part of the fault to slip. If the shallowest part of the fault doesn't slip significantly, you might still get a tsunami, but it's probably going to be significantly smaller than if you had that large shallow slip. That's really what generates the large earthquakes in most cases, so large tsunamis. So really what we want to know geodetically is how much is that shallow part of the fault accumulating strain or accumulating a slip deficit. And we don't really have a good resolution. So here's a model that I've seen in a lot of places popping up. Gina Schmalzli and others put together these two sort of contrasting models where one, they assume that there's full locking at the trench, and so then you have a very large slip deficit all the way extending out to the trench, and they assumed alternately that it might be sort of shaped like a Gaussian in terms of the slip deficit, and therefore there's a very low slip deficit near the trench. And what they showed is that really the on-land geodetic data is only sensitive to the down dip part of this locked area, and so they really have no ability to resolve what is going on at that shallow part. And so this has led to this sort of model: is it slipping or is it not? And I can illustrate that with a sort of a synthetic model. So let's take just a sort of a simplified straight fault, and we can lock it out to the trench here. And then we can have a transition zone and then creep at the plate rate down dip. And then we put some GPS stations just on land, and we can generate, synthetically what would be their rate of motion horizontally on land. And now what we'd like to do is say, well, okay, so say we have that data, we want to invert that, and we're going to try to combine, minimize the data residual plus some smoothing, and then we can add this model norm prior, which I'll show you, allows us to sort of vary the size of the coupling area just to sort of explore what's our uncertainty. So, in this case, what we get is that these red curves are models that all fit the data exactly the same to a chi-squared of 1. And you can see that they have a completely different value of this slip rate or the slip rate deficit at the trench. So essentially we would say our uncertainty is 100%. That means we have basically no ability to tell what's going on. We can sort of simplify that with this shaded area. And the problem that's faced with that everyone is faced with is how should we choose a model? We really want to publish one or a few models, and then the tsunami modelers are going to use that to try to infer what's the hazard. So ideally we would be able to sort of distinguish between these. And one way we could think about doing that is by looking at the frictional properties that we would expect on the shallow part of the fault. So, here's a kind of a synopsis of what we know about frictional properties. We think that they should be velocity strengthening. That would mean that they're sort of stable. There's not a lot of shallow earthquakes worldwide in this shallowest part of the fault. And so that leads us to think that maybe they're sort of frictionally unlocked. And one of the terms that was come up with to describe this is seismic coupling. So we would say there's low seismic coupling on the shallowest part of the fault because there's no release of seismic energy. And unfortunately, this is really unfortunate choice of terminology because geodesists also use coupling, and they've taken this inference of low seismic coupling kind of at face value. So you see models like this where this is the Japan trench, and we see that all along here, basically this model assumes 0 geodetic kinematic coupling. And other models, they might explore maximum, minimum coupling model, but you can see that even in the case of the maximum, it's tapering down to 0 at the trench. So we have the minimum, there's a large area of 0 coupling. The maximum, there's still 0 coupling at the trench. So you would conclude from these models that there's very little tsunami hazard in this part of the fault in Ecuador. But is that really true? Well, it turns out that this has been sort of a debate in the literature for a long time, and it was pointed out by Kellen Wong and Tim Dixon, I guess about 15 years ago, that this problem really comes from a misuse of terminology. So when we talk about seismic coupling, we're talking about a frictional property. We're talking about the amount of the slip that's ultimately released as seismic energy. When geodesists talk about coupling, we're talking about a kinematic term, which is just the slip rate on the fault. So these are very different things. So if it's seismically coupled, then probably it's kinematically coupled. But the reverse is not true, and that really leads to a lot of misunderstanding. So they propose, and we sort of propose that we should just abandon this word coupling and try to be more precise with what we mean. So frictional locking is a much more precise term to say if the fault is locked, that means it has unstable friction, and so it's not going to slip aseismically. It's only going to slip seismically. And when we talk about kinematic coupling, we should just really talk about the slip rate deficit. That's the actual measurement that we're making, or the property that we're trying to infer is really the slip rate. It doesn't actually refer to the friction. We just are measuring the slip. And when you do this, it sort of becomes clear that you can sort of distinguish these two. And these authors pointed out that this doesn't make sense, because if you had a section of the fault that was locked, and then it went back to slipping at the long-term convergence rate, you would have a large area of extension in this wedge. You would have to really put this wedge into a serious amount of tension in order to drive that slip. And there's just really no plausible source of stress that could do that. And so what they argued is, actually this area might be frictionally unlocked, but it's not going to slip. And this shouldn't be surprising. I mean, this is something that's been known for a long time for strike-slip faults. So here's the Hayward fault, and Savage and Lazowski already, I guess, almost 30 years ago, put together this model saying, if this section of the fault is locked, then we can derive a relationship for how fast that shallow creep will be. And so you can actually take this creep observation at the surface and infer something about the width of the locking and the deep slip. So, another way we can think about this is, does it really make sense? Would you imagine that if this section was frictionally locked, therefore the slip rate deficit is complete, would you really expect this entire area around it to creep at the long-term rate? And it's fairly obvious that isn't going to be the case. And there's a relatively straightforward way to predict what that slip rate should be. If we assume that whole part of the fault is frictionally stable, then it can slip in response to any additional stress. So we would say that its shear stressing rate is 0. If it's already reached the yield stress, it'll just keep slipping away any additional stress. And so there's a very easy kinematic relationship that we can use to find out what that shape of the slip rate deficit should look like. And what's surprising here is it really extends out toward the trench. So we call that the stress shadow. This is sort of the effect of this frictionally locked patch on the unlocked area around it, really extending that high slip rate deficit up to the trench. So in this case, it's above like 0.9, all the way out to the trench, up dip of that locked patch. And that doesn't mean that this is frictionally locked in this area. It just means it's not slipping because there's no stress available to drive it. So we can actually apply this to try to fit data, and that's what I want to show you, sort of an interesting model for how to do that. So we can do it by trial and error. This is something that Roll and Bergman did quite a while ago, where they took these patches that are white and said these ones are frictionally locked, and then we'll just predict the slip rate everywhere else using that simple sort of stressing rate relationship. And you can see that even with relatively small locked patches, you can get a large slip deficit developing, especially on that up dip part of the fault. And so the key is we actually, we looked at this and we said this is a linear relationship. So stress and slip are linearly related. This matrix here, this is something that you already have. This is part of Okada. This is like the strain matrix, and then you can just convert that into shear stress. And so if we said, well, on a frictionally stable part of the fault, the stresses shouldn't be decreasing. They should be at least stable. And on the locked parts of the fault, the stresses will be increasing. So we can basically impose this requirement that the stressing rate has to be non-negative, or is greater than the background stress input. And we can turn this into a linear inversion. So we can take this and we can say, these models aren't plausible. Let's add a constraint in our inversion that says we want non-negative stressing rates only on this part of the fault. And when we do that, we get the blue region of plausible models. So what you see is suddenly our uncertainty has gone from 100% at the trench down to less than 20% at the trench. So now, even though the data don't have resolution, the model has resolution because we've imposed physics into it. And so now we know, we can say relatively for certain that this part of the fault in the long term shouldn't be slipping more than 20% of the plate rate. And this is very analogous to that Hayward fault model where they had a similar relationship. Depending on the locking width, you'll get a certain amount of creep rate that's going to be much less than the long-term rate. And so, what we can do is we can try out this model on places like Cascadia. So here's our model without constraints. So this is sort of the Schmalzli et al. Version, where we say here's a maximum model. This is maximally coupled all along the trench. Or here's a minimum model where we go all the way down to zero coupling along a significant part of the trench here. And so we would say our uncertainty without these stress constraints is 100% in this area here. And if we impose the stress constraints, now, there's still a variation in possible models, especially in this area in Central Oregon, where there's not as much deep coupling or deep locking, frictional locking. But in this area offshore Washington in particular, our uncertainty has gone down quite a bit. So it's gone from 100% to maybe 20 or 30%. And so we could say definitely this part of the fault is not slipping at a fast rate in the long term. And so for the Japan trench, it's actually even worse without the stress constraints because the width of this fault to the trench is much larger here. And so the two competing models, we could have very low slip rate deficit over a very wide area, or the whole thing could be locked. And geodetically, these are indistinguishable. So we would say over this entire area, our uncertainty is essentially 100%. But particularly in the Tohoku region, we know there has to be something going on. And when we put the stress constraints, sure enough, we see that that deeply locked patch that's imaged well by the geodetic data extends its stress shadow up to the trench. And so our uncertainty in this region is actually not 100%, it's more like 30 to 40%. There are some regions that remain high uncertainty because they don't show a deeply locked patch, or maybe it's because we don't have on-land data in this area. So we do have some remaining areas of high uncertainty. And that actually helps us target where we should put our seafloor stations, right? So you might be skeptical, and fortunately there are GPS acoustic data existing in this area, so we can try validating these. So here's the two models based on only the on-land data, and if we add the GPS acoustics, you can see how much they change. So this one actually changed quite a bit. You can see now it's sort of outlining around the area where the GPS were collected, and it still is trying to fight, really still possible to fit these data even if you have zero slip rate deficit at the trench. But you can see that this one, if I go back and forth, this one didn't really change that much. And here's the difference. So we could say the stress constrained model really showed up quite a bit better, better result here. And of course, this is the area of the Tohoku earthquake, so that also gives us some validation that our model is sort of seeing the right things. This is the area that eventually did slip with large slip at the trench. So we know that there must have been a slip deficit there. So what this tells us is that most kinematic models of interseismic slip don't take this into account, and they're really kind of missing this fundamental physics. So we can actually, by imposing this physical constraint, we can get a much better resolution, and we avoid this sort of impossible or implausible physical prediction where we have high coupling followed by low coupling. And what this tells us is that the slip rate deficit is high close to the trench, and unfortunately, I have to say that global tsunami hazard might be underestimated, because a lot of those models that were sort of naively predicted with zero slip rate deficit at the trench have been taken by tsunami modelers and then used directly to generate their tsunami hazard scenarios. And so they're using some bad inputs in those cases. And what we really need to do is say, please don't use those anymore. Use only the highly coupled, high slip rate deficit models. And what's interesting is we can infer this for the most part without offshore data, but in some areas where there isn't that deep frictional locking, our uncertainties are still high, and so that helps us sort of target where we should put those GPS acoustics in the future. If we're going to look for creep, this is certainly going to be a better place to look than here. And that also tells us something about the uncertainty that we need. So the instrument design, we've got to get better than a centimeter a year, or we're just, it's not going to add anything new because our resolution isn't really as poor as we originally thought it was. So this is my takeaway for Cascadia. Put the GPS acoustic offshore Oregon, offshore Washington. It would be interesting, but it's not going to tell us much compared to this model because we can already say that it's going to be highly coupled or high slip rate deficit. So that tells us a lot about the slip in the shallow part of the fault, but it doesn't tell us a lot about friction. So I haven't made any predictions about whether those highly coupled or high slip rate deficit parts of the fault will slip seismically. So we don't really have the ability to say that directly from this model because those parts in the stress shadow, their frictional properties are sort of hidden by the deeper lock parts. So we have to look for some activity on the fault to get some clues about that. And I'll take you to the Mentawai patch. This is in the central part of the Sunda megathrust offshore Sumatra. And historically, what we've seen from paleoseismic and paleogeodetic data is that it ruptures in these sort of pairs of magnitude 9 earthquakes, sort of this southern section and this northern section here separately. And following the great 2004 earthquake in the northern part of Sumatra, we started getting these ruptures, 7 to 8 magnitude earthquakes. First one here, 2007, followed by these sort of sequence of maybe aftershocks, some of them with very strange slip distributions. This one had a gap, so it slipped 2 different parts. A tsunami earthquake here, large slip at the trench. But we really haven't had that full second rupture that we're sort of anticipating. And it was really interesting, and there's sort of a lucky thing that happened. There's this earthquake here in 2008, and it was actually well recorded by the GPS network that was installed there and also by INSAR. So we have these islands here, and it gives us really nice resolution to be able to see what's going on, and we can actually sort of learn something about the mechanical properties of the fault. So here's our geodetic slip inversion. This is done by Reno Salmon, a really excellent student in Singapore that I got to work with. And so, geodetically, we see that there's this sort of circular rupture here. The INSAR is just kind of nicely highlighting that rupture. And what we can see is that we have really good resolution. The GPS is pretty good, and if we add the INSAR, we really have great ability to resolve these patches. So we know that we're imaging it in the right place. And when we look at the afterslip, surprisingly, the afterslip is really overlapping the coseismic slip. And we thought that was kind of strange for a while, and we were thinking about this like, the coseismic slip is here, and then we've got 2 sort of patches of afterslip. The down dip one is not really overlapping as much, but the up dip one really significantly overlaps with that coseismic slip. But it turns out this is actually not that surprising because this is what we have if there was a isolated frictional asperity. Then when it slips, this area that was held back isn't going to be held back as much, and so you would expect to see afterslip in this area, and you might also get coseismic slip extending up into this region as well. So you would expect that you would see this overlap in this up dip area where there's frictional stability, but also a high slip rate deficit. And so that gives us kind of a nice way to understand how this is happening. And when we think about these asperities, maybe they really are sort of this kind of patchy network of frictionally stable and frictionally unstable patches. And so maybe these things can rupture sort of in a piecemeal way, sort of independently from each other. And the really important question to ask ourselves is are these gaps between the frictional asperities going to be detectable? And how might we sort of understand how, when do these asperities link up and when do they not? What I have to say is that if you have this many asperities this close to each other, you really are not going to get much ability geodetically to distinguish them, because they're going to have essentially full kinematic coupling or full slip rate deficit for this whole area. So we're not really going to get much ability to distinguish them unless there's a wider gap between them. And in fact, we do see a little bit when we do this stress-constrained slip deficit model. We do see a little bit here of a lower slip deficit in that gap. This is right in that area where the earthquake occurred. And this turns out to correspond with a subducting fracture zone that might be producing a lower slip deficit. It might be sort of a fractured part of the fault, and so it's not able to sustain that frictional locking. And we see that in other areas as well. And these are really interesting because they also are associated with patterns in previous earthquake ruptures. So here's an area in Simeulue and Nias. So in 2004, we have the Great Anamanache earthquake extending off to the north here, and in 2005 an 8.6, and it had low slip in this area that turns out to be another subducting fracture zone. And then both of these earthquakes were sort of isolated from each other by this other subducting fracture zone right here. And it turns out that this subducting fracture zone has halted previous large ruptures as well, just like the one in the Mentawai patch that has sort of isolated those two asperities. And so we can say that, this might be one of the ways that we can actually understand how these earthquakes rupture if we have some idea of their structure. And it turns out there's a lot of geophysical information here that shows that this fracture zone is creating some lateral ramps. So the interface, the plate interface, kind of steps up to the fracture zone and then steps down on the other side. And so it could be that those ramps are sort of structurally controlling that rupture pattern there. And now this is a familiar earthquake to some of you. This actually happened just as I was leaving Scripps, and we wrote a nice paper just kind of quickly looking at these data. Turns out, this is one of the best recorded co-seismic slip events on a megathrust. And I really want to emphasize, the Himalaya, the main Himalayan thrust is a megathrust. It's on land, but it functions just like a megathrust. And so we have great geodetic resolution here. And what we could see is this area, we can see where it uplifted and where it subsided, and we can make a very nice, excellent model of the slip that occurred on the fault. And if we compare that with the geology, Kathmandu is located in this sort of interesting location where this oldest material, which is in pink in this model, kind of takes a dip to the north, and there's a little bend in this the location of the anticlinorium that's uplifting the oldest material. And so if we take that, and what my collaborators in Singapore did is take this geologic information and make a 3D structural model of the main Himalayan thrust. And so this is work by Judith Hubbard and Rafael Almeida and others, and they sort of showed how you can really get a nice image of where that mid-crustal ramp is. There might be a secondary ramp here as well. And when we put that together with the geodetic data, if we take this, here's contours of that model, and we take that model and use it to invert for slip, you see that the slip is really nicely bounded by these ramps. So just like in Sumatra, it looks like maybe this is a little asperity that's being isolated from other parts of the fault. And what's interesting is that the average slip on this section is about 4 meters. That's almost exactly what you would expect since the last earthquake that caused similar damage in Kathmandu, which was in 1833. So maybe this is kind of a similar case to Sumatra, where we have these structural barriers that are isolating different parts of the megathrust from each other. So we would say that, structural, the fault structure or the fault geometry is really key to understanding that. So even if geodetically in the interseismic period, what we see is basically full slip rate deficit across the whole fault, we can still infer something about where the ruptures might be in the future if we have this structural model. So, okay, so now there's a secret part 3. I've talked about interseismic slip, and I've talked about coseismic slip, but what about in between? So, not all slip is seismic, and it's not all interseismic. We sometimes have unusual behavior like slow slip events. And this is a really interesting coral. This is actually also in Simalu, and Aaron Meltzner and others from the Earth Observatory of Singapore went out here, I guess almost 10 years ago, and they found these corals that have a very curious pattern of growth. So normally what happens with a coral is it grows up to the level of the low tide, and then it sort of grows out flat. And so by looking at that, where that coral grew up to, you can actually infer what the sea level was at the time in the past. And so what's happened with this coral is it grew up to sea level, and then it grew nearly flat, maybe just slightly sloping up for quite a long time. And then suddenly it started growing up at a much faster rate. And it didn't just suddenly uplift, because it didn't grow. Usually these corals will kind of wrap around if they're uplifted or subsided so that they can grow up to a higher level. It looks like it actually took several years to grow out to that higher level. So it looks like there was maybe some slow subsidence followed by faster subsidence. And now this coral is sitting about 1 meter above water, so obviously there was something dramatic that happened that threw it out of the water, and it died. So you can see there's a chainsaw cut through this coral here. What they did is they take it back to the lab, x-ray it, date it geochemically, and you can actually date these corals very precisely to about a year uncertainty. And so what we can see is there are several corals found along the island that did a similar thing. They grew slowly up, so these elevations are flipped so that we can see the subsidence. So these corals were slowly subsiding for about 100 years, and then at some point around 1829, they suddenly started growing faster. And so we would say, here in gray, these slower subsidence rates, and in red, for about 30 years, they suddenly started subsiding much more quickly. So could this be like a slow slip event? It was sort of talked about around the department for a long time, but we never really were able to figure it out until another student, this student Rishav Malik, who's really great, and I was really lucky to get to work with him for a couple of years while I was there, sort of looked at this data again from fresh eyes, and he was working on the stress shadows model with me as well. And he said, well, maybe we can actually try to make a geodetic model of the slip just with this one single data point. So we have the set of corals at one location away from the trench, and we can see what do they tell us about the fault slip. So for the first period in gray, we've got this sort of very small subsidence rate, and then we also know this is the area of the Neos earthquake that had a large amount of afterslip in the shallow part. So we can suggest that probably the shallow part has to be frictionally unlocked, but the deep part is probably locked. And so it turns out if we make that set of criteria, then there's a pretty narrow range of models in gray here that are constrained. So just with this one subsidence rate, we can do a pretty good job of imaging the part of the fault that's locked and the part that's unlocked. And now when it started subsiding faster, if it was a deep slow slip event, it would produce uplift in this location. So it has to be a shallow slow slip event. So that means it has to be in that same area that had the Neos afterslip. So it must be sort of somehow a slow slip event occurring on a frictionally stable part of the fault, which is pretty surprising. And even more surprising, this earthquake or this slow slip event lasted about 32 years. So that's definitely the longest slow slip event yet recorded, and it was terminated by an earthquake in 1861. So in 1861, this part of the fault ruptured in something similar to the Neos earthquake. So quite a surprising result there, and it's really pretty amazing what the stress constraints, in addition to just a single geodetic data point, can tell us. And this is also just in press in Nature Geoscience. So take a look. This paper and the stress constraints, stress shadows paper will both be out, I think, in the same issue. So take a look for those in the next couple of weeks. What we thought is one possible method that we could produce this. We searched for a while, and what we came up with is the fluids on the fault. They really control if you have a conditionally stable part of the fault. So here's the frictional, the velocity strengthening and velocity weakening zones. And if we make this part of the fault just conditionally stable, so it's sort of almost unstable, but it's actually just slightly positive A minus B, and then we increase the fluid pressure, then that part of the fault is going to lock. And then you get slow recovery, and once the slow slip event starts, if you allow that to sort of slowly recover the fluid pressure, that gives you sort of a variable parameter that you can tune to say how long that would last. So if there's fluid flow into the fault during the slow slip event, that is a mechanism that would allow that slow slip event to take such a long period of time, because kinematically it should probably rupture more quickly. But if there's a fluid recovery component, then that is something that allows it to take a longer period of time to slip. So this is certainly not the only hypothesis for how to explain such a long slow slip event, but it's a possible hypothesis that we sort of have the fault gets drained in some way during an earthquake or during passing seismic waves, cause that fault to leak. Then it gradually recovers, and when the fluid starts recovering, you get a very long duration slow slip event as that poor fluid pressure recovers. And this is a mechanism that would allow you to have that slow slip event even if it's a velocity strengthening fault. So I think it's an interesting model. And the other thing that I really want to say again is we're looking at some unstable slip. And that's what's really giving us information about the fault. So if we're thinking about what to do offshore, I really want to emphasize, I think transient behavior gives us the most information about the fault, about the friction, about the material and mechanical properties. Because we know that most of the shallow part of megathrust is in this stress shadow. So in the interseismic period, if we're just looking at the sort of long-term data, time averaged, we probably won't see very much because it can't creep at a long-term rate that's very fast. But if we're looking at transient behavior, that gives us really this key information about the friction on the fault that allows us to develop these mechanical models that really help us understand what is happening. So then just to sum up again, we have Stress shadows. Everywhere there's a frictionally locked patch, that's going to cast a shadow that might be unlocked or might not be, but either way, it's not slipping. And I really want to just to emphasize again, as much as you can, I know it's hard, but try not to use the word coupling. You can see I still have it in my figure here, but you know, I do my best to try to say slip rate deficit, or at least just to say kinematic coupling. And definitely make sure to disambiguate locking is a frictional property, but when we're talking about kinematic models, we're talking about the slip, not the friction. And then, you know, I think that imaging fault structure is one of the keys to really understanding how these earthquakes rupture over time. And, you know, what we've seen in Sumatra and also in Nepal is that ramps and other structural boundaries can really control how those ruptures occur, not just once, but sort of repeatedly over time. And so when we see these asperities rupturing in systematic ways, there's really likely to be some kind of a structural control there that's determining how they tend to slip over time. And finally, transient slip. This is really should be our target, I think. Gives us the most information about fault properties. It's harder to see, maybe not everywhere. It's kind of a trickier target, but when we can find that type of behavior, that's really our golden opportunity to learn something about fault friction. So just thank you again to all my collaborators and the students and mentors and many other people that I was lucky enough to work with over the last few years. And thank you for listening.
Thanks, Eric. That was a wonderful talk. We definitely have time for questions, so you guys can either use the raise hand, which I think is in participants, or just let me know in the chat that you have a question. And Dave, go for it.
I have a question about the Gorka earthquake. So during that earthquake, there was no shallow slip. So I guess it's one of two possibilities. Either, well, I guess it would have to be locked during the interseismic period, or there's something about that ramp that kept the slip from going shallow. I mean, how does that work there?
Yeah, it's tricky. There was a tiny bit of shallow creep on like a sort of a fault that's believed to be inactive. So there's, you know, it's kind of funny, but it was just a few millimeters. So yeah, so it looks like the shallow part of the fault is probably for the most part locked, or at least enough of it is locked that it wasn't able to slip. So I think, you know, that should actually challenge our commonly held belief that most of the shallow part of megathrusts is frictionally stable. So, you know, in all of this, I said, well, let's assume that the shallow part of the fault is frictionally stable, and then what can we do about it? But, you know, it might be that it's all locked, or at least that in many places it's locked. So
like a good target for, you know, more current GPS measurements for a long time, see what happens.
Yeah, well, I mean, there is a lot of GPS there, and what we see is it just looks locked right up to the trench. So,
yeah.
So, you know, yeah.
Thanks.
Alice, would you like to ask your question?
Yes, it's long. I have two questions. I put them also in the chat, so I don't forget. It's a bit late here. So the first one was about first really inspiring talk. I have two questions. The first one was for Cascadia, and we did some dynamic rupture modeling for Cascadia, and I think some of the conclusions we came up with that would be really interesting to compare to your preferred model that you had on your slide. So, for example, we showed also that we would assume that the slip weakening behavior, or at least a moderate slip deficit close to the deformation front, is necessary if you would like to reach dynamically these margin-wide ruptures. While at the same time, if you're then incorporating the offshore data, that I think you didn't comment on that too much, but if you're including that, we see that we do need some long arc heterogeneities. And that brought me to the question, what do you think the resolution is in this preferred model along arc?
Yeah, so, you know, along the arc, I guess there does seem to be some variation. There certainly is a deeper frictionally locked patch in this area around Washington. And I think that's been imaged well by others as well. Is that in Oregon there might be this sort of more gradual trend, gradual change in the coupling, but it doesn't seem to be as large and as deep as the shallow part. So this is the model resolution map here. So it's about 50% around these contours. So we can't really say better than 50% whether it's fully slip deficit is 100% there, or if it's as low as 50%. But it can't really be lower than that probably. And in this area up in the Washington area, it's almost certainly going to be highly kinematically coupled, but yeah, we don't know about the friction. So it still is still a mystery about the friction. And I would say in this area it might not be a great target for GPSA, but it's probably a great target for pressure sensors because we want to look for those transients. That's really our best hope to find out something about the friction there.
Yeah, good point. And the second question is shorter. It's about Mentawai. So from the hazard context, I think the big question is if the next big one there would be having a shallow or deeper hypercent, at least if you're talking to the tsunami community, and they're kind of typical probabilistic tsunami hazard assessment, bearing source locations. So could you comment on this if you had any implications from your analysis on that?
Like a hypothesis of whether there will be a shallower or a deeper?
Yeah, because that would really impact like how severely Padang will be hit. So.
Yeah, I mean, I guess it's pretty tough to say, but what I would say is the 2010 tsunami earthquake was a magnitude 7.8, but it really didn't have much geodetic signal. It was pretty tough for the modelers to get a tsunami that was large enough based on the geodetic signal, because it's so far offshore. Even though there's the islands, it didn't have as much geodetic signal as we would expect for that size of an earthquake, because all of the slip was really concentrated right at the shallowest part. So I would say, the coral paleogeodetic data along those islands indicates magnitude 9 earthquakes have occurred there in the past, and to get that much subsidence or uplift, depending on the location, that has to be a deeper earthquake, I think. So there has to be the potential for a deep earthquake to occur to generate such a large amount of subsidence on the islands. But yeah, it doesn't rule out the possibility, again, of having those shallow earthquakes. They're almost sort of like invisible earthquakes to the paleoseismic data. So that's pretty tricky to tell.
Thanks.
Eric, do you have a question? Sorry, Tianzin, we'll get to you in a sec.
Sure.
Eric?
I'm trying to unmute myself. Hey, Eric, really nice talk. I have two questions. The first is that with the physical constraint that you put to this kind of modeling, how far away or how close you have to have a GPS station in order to put good constraints on the what do you call slip rate deficit ratio?
Mm-hmm.
Like how does that compare to when you don't have the physical constraint? And my second question is, well, it's like from the physical constraint you put, it feels like almost all the earthquakes, really big megathrust earthquakes, all of them are going to rupture to the trench, right? Anything to say about it, or is that really the case?
Yeah. Okay. So the first question is, it's tricky to answer because it's not simply about the distance between the GPS station and the part of the fault. It's also about the existence of other parts of the fault that are locked, because the constraint is the relationship between different parts of the fault. So in this area in Cascadia, where we have this deeper frictional locking that kind of extends all the way up to the coastline, then we get really good resolution offshore, because we can say, if this part is not slipping, then the shallow part is also not slipping. But in Oregon, where there isn't as much of that slip deficit near the shoreline, then our resolution offshore is worse. So here you would say it's, the uncertainty is quite a bit larger because we don't have that deep locking to kind of, if we have that deep locking, we know it has to be not slipping at the trench. But if we don't have that, then we don't really know.
So it kind of depends on whether the well-constrained part by the data has slip rate deficit ratio at that place. Okay.
Yeah, exactly. Yeah, you can think of it as like a way of smoothing
over to the trench,
the fault up to the trench.
I see.
In a kind of a physical way. Yeah, and the second question, sorry, so not all of the large earthquakes do rupture up to the trench. I guess we don't know for sure whether that's true or not, but the Nias earthquake in particular was one case, was an 8.4 magnitude earthquake, but the tsunami that it generated was very small, and then the GPS instruments imaged like quite a bit of offshore up dip after slip. So it looks like that's the case where the earthquake might not have ruptured all the way up to the trench. But we don't know for sure. It could have ruptured partially up to the trench or something. But it looks like there are possibilities for either having large slip at the trench or not in different cases.
Awesome. Yuri, go for it.
Yes, Eric, so great talk. I have a question about your coral time series. Perhaps you can go to that figure where you had a summary.
Is this one?
Yeah, so in the period which you consider to be normal, interseismic rate, there that you infer to be the accelerators.
Yeah, so coral data is really tough to interpret, and so it's a real challenge. And you can talk to Aaron about it in detail. But I think what I understand is they're looking for, so the coral will continue growing up and up until it gets like a bad year, like an El Nino or something equivalent, where there's an unusually low tide, and then it will die back. And so the dieback dates are actually the darker circles here. And so we're not actually fitting the subsidence rate to all of these elevations, but we're fitting it to those darker dots. And so you could have like a dieback followed by rapid growth. So that might be something that happened here. So there's sort of different pieces of the coral that was at different elevations, but it had died back, and then it's growing rapidly up to this elevation. And then it was sort of held at that elevation by the tide. So in these areas where it was growing rapidly up, it wasn't actually that it was hitting that elevation. They're looking for those indications of a dieback, that was the actual tide at that time. And you don't get that every year, so it's sort of intermittent. And so so it is a tricky interpretation in these cases where the growth rate might be similar to the subsidence rate, whether it's actually growing back, dying back or not. I guess I just have to sort of trust their interpretation that they found these cases on several different corals around the island in different locations, and they really believe that this was sort of, these corals did grow at a stable rate that was controlled by the tide and not by other factors. But it is tricky. Yeah, coral data is certainly messy. So this is just one observation essentially of this possibility for this strange behavior.
Okay, and my other question is about the model that you're using to compute stresses that are released interseismically by allowing that slip on the stress shadow. And the model, if I understand it correctly, comes from just this deeper dislocation that approximates the slip of the part of the megathrust below the seismogenic zone at plate rate, presumably. Mm-hmm. Some would argue that perhaps is not a very physical model. So I was wondering if you considered other loading situations. For instance, you have your accretion wedge, there's a backstop, and there's something that drives it on the side of the downgoing slab. And in that case, I think the stress and rate may be quite a bit different compared to that comes from the deeper dislocation.
Yeah, so There's another similar model by Matt Herman that was published a couple of years ago, and they've done a similar thing. They're actually using a finite element model, so they drive it from the far field and kind of compress both sides, and so they've got a different type of loading scenario, and they actually come up with a very similar result as ours. So I think there could be a slight difference. It would relate to sort of the compressibility of that downgoing slab, whether you have, there might be additional slip in the interseismic period that's driven by just that slab getting shorter itself due to compression. But I think essentially the difference is going to be pretty small. It is a different boundary condition, but the result is more or less similar.
Thanks.
Yeah, I don't exactly have a comparison figure for you, but it's quite similar.
Thanks.
Tiente, you want to go for it?
Thanks. A very nice talk. Thank you so much, Eric. I have a more basic question because I'm not from this field. I didn't quite get how frictional locking is different from slip deficit. Can you further explain it?
Sure. Yeah, that's a good question. So when we talk about frictional locking, we're talking about the frictional stability of the fault and whether or not it's going to slip in response to. So if the fault is frictionally unstable, that means that if you start slipping, then the friction drops and it's going to have a runaway slip. So that's like what we see in an earthquake. That part of the fault is frictionally unstable, and so if that part of the fault is not in an earthquake right now, it must not be slipping, because if it were slipping, it would start to run away seismically. So that part of the, we say it's friction, it's not starting to slip yet. When we talk about slip rate deficit, it kind of doesn't depend on the friction. We're just saying what rate is any part of the fault slipping at this time. So we could say, this part of the fault is slipping or it's not slipping. And if it's not slipping, then we could say, do you think that's because it's frictionally locked? But we don't know. It might not be slipping because there's not any stress to slip. So, if the fault is not slipping, that doesn't tell us anything really about the friction. It tells us either it's frictionally locked or there's no stress available to drive it to slip. If it is slipping, then we can definitely say something about that part of the fault. If it's creeping, then it has to be frictionally stable, because a frictionally unstable fault can't.
Okay, and is it true that most of the parts near the trench of a megathrust is usually frictional stable or frictional like a sleep strengthening? Is that true?
I don't know if it's true.
Okay, so it's
Okay.
So it can either be frictional stable or unstable. We don't know. It depends on individual trenches and the condition there.
Yeah, probably so. And it's also possible that these types of frictional properties are more complex than, it's not just a simple binary thing. So it could be that they're frictionally kind of conditionally stable. So it gets more complicated for the real faults, but yeah, we don't know for sure. I think we have kind of thought for a long time that they should be frictionally stable. There's kind of mineralogical evidence, and the seismic evidence suggests they should be stable in a lot of areas. But the same evidence applies to strike-slip faults, and we only see creep on certain faults in certain cases. So it's kind of still kind of an open question, I think, whether they're frictionally stable or not.
And the way you are estimating the tsunami hazard here is to estimate its slip deficit to see like how much slip it may happen in a megathrust earthquake, right?
Right. It's a kind of a worst case scenario, I guess.
Gotcha. Great, thanks.
Wenyan, you have a question?
Yes. Well, thanks, Eric. Haven't seen you for ages.
Yeah.
Great talk. I guess my first question is, of course, the model results have pretty important implications, in particular regarding tsunami. But have you considered about putting in split faults and such? If so, how would that impact your model results? How does that impact your slip deficit results if you put in split faults?
Okay, so it's an interesting question. So for splay faults, I don't know. I think if you wanted to have the model where there are several faults and each of them can be slipping, then they're going to compete with each other to sort of produce that geodetic signal on land. So it's going to be really tough to distinguish those. I think we're really pushing the model resolution as much as we can already with the stress shadows model. If you want to have multiple faults offshore, then it's going to be really tough to resolve, which one might be slipping. It certainly would very strongly affect the seismic and the tsunami hazard because, depending on which ones slip and their dip as they come up to the surface, that really affects how much uplift you might get and the tsunami size and everything. So certainly is a really important hazards question to image those. But I think, I guess what I would just say is that the stress shadow framework kind of suggests that none of them are going to slip very much interseismically, regardless of what's happening frictionally with them. There's not a lot of stress or deformation available in that sort of up dip corner of the wedge to drive a lot of slip interseismically. But certainly when the earthquake ruptures and you start propagating that stress upward, you could get slip on various ones.
Right.
That we
yeah,
do.
so because for Mantua, one hypothesis regarding the tsunami, not just this one, but the other one is involving possible split faults. And since you're working on this region, I thought there might be some insights. So another question / comment is, if I'm understanding this properly, there is a lack of validation of what you're proposing because of a lack of offshore observations near the trench. But like you pointed out, Nepal earthquake was an excellent example to draw analogy to subduction zone. And as a matter of fact, there were a lot of camping GPS operated by the Caltech group for a long time. And so according to the coupling rate, kinematic coupling rate, it basically has slip deficit all the way to the front. But the Nepal earthquake actually did not rupture all the way to the front. So perhaps a simple way to understanding this is to use part of the GPS data, but impose what you're doing and calculate what it should be, and see if would produce the same coupling rate. And if that is the case, then perhaps previous estimate of that region was actually an overestimation because of the idea of the kinematic coupling equals to a frictional locking.
Well, I guess I would say for the case of Nepal, because we have the GPS data at the trench or close to the trench, we can say pretty certainly that it is not slipping there interseismically.
Yes.
And then it didn't slip seismically, but that's not in contradiction with the model because the model doesn't say anything about the frictional properties. It just says it's not going to slip interseismically.
Yes.
And then it's really up to the details of the rupture and the fault properties, whether it permits a complete rupture or partial ruptures. In this area in Nias as well, you can see that there was like a deeper earthquake followed by a lot of afterslip. That's quite a different case from Nepal, where there was a deeper earthquake followed by no afterslip in the shallow part.
Right. So no, what I'm pointing out is
coupling map, the kinematic map would look the same in both cases.
Yes. So I think just to back up your current model, you can just use part of the GPS from the Nepal, not using the parts near the trench, but only use the backward ones. And it's very likely you will produce the same coupling model kinematic coupling model as what they use with all the GPS. And so if this is a case, then you have a much stronger argument to back up your proposed model, right?
Yeah, I see what you mean. Yeah, actually, we did
That's
that.
what I was trying to
That
do.
was in an earlier paper that was Raphael was the first author on that. So we did look at that for Nepal and also for Nankai. I think maybe I didn't put it in there. We actually looked at that in a forward modeling way to sort of see what rate of creep is possible in Nepal, and we kind of concluded that not much creep is possible in Nepal.
Right.
But we did also have the validation from the seafloor GPS in Tohoku, and in that case, the model is validated really well. So
Right.
yeah, I think but it's a good point. We could try running the model in the same way by sort of simulating an offshore megathrust for Nepal, and I think it would give us kind of the same result in this case.
Yeah, I think that's just a strong support for what you're proposing. Well, thank you.
Yeah, thanks.
Ignacio, you have a question?
Yeah, thank you, El. Thank you, Eric. Great talk. So I'm very identified with the comments that you were saying about what is going on when you were trying to, for example, generate a synthetic earthquake and you don't know what to put in the shallow part. Actually, I have been doing some synthetic earthquakes in the South China Sea and in Chile, and always we have the talk with the co-author about what we put in the shallow part. So and not only because of the slip, but also related with how is the ecosysmic deformation close to the shallow part, and furthermore, how the water react to short length deformation of the ecoseismic. So there are some things which are very easy to apply for the ecoseismic deformation and the water movement. But as far as the slip is concerned, I think that is one of my weakness. And for example, what we are doing and what we did last year was to try to work with a conditional random field in order to model another problem for bathymetry. But I wonder if, for example, we can apply a conditional random field in order to try to model the stress shadow and try to generate a conditional random field conditional to what is going on in the deeper part and try to establish a random model for the stress shadow of using your model, basically. What do you think?
I guess you mean like you could generate sort of a random distribution of the frictional properties and then predict the slip based on
Exactly.
that. So yeah, that's a really interesting idea. I think
and conditional to what is going on in the deeper part.
Yeah, it's kind of similar to I think the model I showed by Roland. So what he did here is they're kind of randomly choosing these white patches to be frictionally locked.
Mm-hmm.
And then they predict the stress shadow or the slip deficit around them. But you could kind of invert that and think of this as the possible areas that might slip coseismically. And if you had only this part is frictionally locked, but then you might get this much coseismic slip up to the trench.
Wonderful.
Versus
exactly.
if the whole area was frictionally locked, you would get a lot more slip up to the trench.
So the stress shadow is based on a diffusion equation. How that it works? I don't know how that works.
It's just based on this equation. So basically, this is the driving stress. So Yuri was talking. This driving stress comes from the deeper part, the sort of the backslip model of driving stress, and then we have. This is basically the strains that come from Okada or your triangular dislocations or something. And we just impose this requirement that it's not releasing more stress than it's accumulating.
Nice. Thank you, Eric.
Sorry, you have a question?
Hi, Eric. Nice talk. I have two questions. First, it's do you mean that at the shallow portions of those subduction zones are more likely to have stress shadow, or is there any? I mean, so there are many, I saw many models in working model. Maybe I bet they kind of overestimate the locking ratio or some kind of, there are more, the actual locking state is probably more localized than those models should, right? Not only for, I mean, not only for the shallow part, but also for like the deeper portion. Even even those cover have even those portions with better geodetic coverage. You think that's
right? So you're kind of saying, like, in this example, for example, the locking is only the white area, but what we would call the coupled or the kinematically coupled or slip deficit is all of the blue. So the white area is much smaller.
yeah. I mean, is this also common in other places? I mean, in places other than the near trench area of subducting zones?
It's really hard to say. I mean, one of the problems with this kind of model is, it could be this way, right? But we don't have the resolution necessarily to say for sure. So it could be that more of this area is actually frictionally locked.
Yeah, but let's say for the Nepal earthquake or for other earthquakes where there are good the geodetic data coverage, do they also have this like possibility?
Yeah, we do. I mean, so for the Nepal case is a great example. So the kind of the accepted model for Nepal is that the entire megathrust is frictionally locked from the trench all the way down to the mid-crustal ramp, all the way along it. That's kind of the default model for that subduction zone, for that megathrust. But another model is that it's just a whole patchwork of frictionally locked small pieces, with even the majority of the fault might be frictionally stable, but because there's so many of those small frictionally locked patches, you can't tell. So geodetically, we can't distinguish between those two cases because the stress shadow sort of interpolates that slip deficit around the locked areas. So geodetically, it's not really possible to distinguish those two. So I think we don't really know if the majority of the fault is locked or not.
All right, thank you.
Tricky problem.
Another question is, I wonder, like, how much would the stress shadow affect the tsunami potential? Because I think many subducting zones near the trench, the dipping angle it's pretty small, right? It's like some kind of, so even like the portion under the shadow, if it's slip during earthquake, would that really change something about the potential tsunami?
Yeah, I don't know. I mean, I think the point we want to make in this model is that we should consider the slip rate deficit to be high. So there's at least the potential for a tsunami kind of anywhere that you have a down dip locking, because the down dip part is going to hold back the shallow part. But as far as the details of what actually happens on that part of the fault is tough to say, because again, we don't know that much about the frictional properties there. So it might be that it's frictionally stable. You get a big earthquake down dip and just after slip up dip. That's what happened in the Nias earthquake. Or it might be that you get a big earthquake and it drives slip all the way up to the trench. And somehow, whether it's just the slip on the trench or you have other splay faults or pop-ups or something, you can get that large slip. We don't know a priori from the geodetic data which one is going to be, but what we know is that there's the potential for those large slip events to occur. If you have a model that has no slip deficit at the trench, you're saying, I think there is no potential for a tsunami to occur in this location. And I think what we're really trying to argue against is, don't make such a strong statement about no hazard, because you can't say for sure there's no hazard. It might be low hazard, but it also might be high hazard, and we have to be really cautious when we make these models and try to consider the worst case. So.
Sure. Thank you.
Yeah. Thanks.
Any last questions for Eric? I think with that, we'll wrap up. Thanks again, Eric, for the really awesome talk. Next week, we're going to have an internal seminar with Rob and Yehuda. So hope to see everyone there. And yeah, thanks again, Eric. Thanks everyone for attending.
Thanks so much, Al. Thanks everyone for coming.
Great talk, Eric. See